The purpose of this video is to talk about application problems related with multiple integration. We will talk about chapter 14, section 4, where we're going to talk about mass of a simple lamina, center of mass, and moment of inertias. The first thing is going to be reminding us about the formula for finding the mass of a simple lamina. So let's recall, if rho is the continuous density function for a simple lamina, then the mass of this simple lamina is going to be given by a double integration. Then the mass is given by m equal to the integration of this continuous density function rho, and say this is a function of x and y, with respect to the area of this lamina over the region R. So the region R here is actually the area, the surface area of the lamina, of which you are interested in finding the mass. Once you have found the mass of this lamina, you can always go ahead and start talking about the center of mass. In order to know the center of mass, we still do several variable integration. We find a thing called mx, where the formula for finding mx is the same region, and you are doing a several variable integration of the function y times this continuous density function rho xy with respect to the area. And we find one other constant my, and that's given by the same region of integration, but instead you integrate x times rho xy with respect to dA. Once you know the values for mx and my, you're going to go ahead and say that the center of mass for this lamina that we are playing with is going to be the coordinates of a point, and those are mx over the mass m. So the x-coordinate is mx over mass m, comma, my over the mass m. That's the center of mass of the simple lamina. So let's try to use this concept and solve some problems. Our first problem is asking us to find the mass and the center of mass of the lamina bounded by the graphs of the equations for the given density function. As you can see, the density function in this problem is a constant density function, rho is equal to k, so it's a continuous density function as well. Whereas the boundary of the lamina is given by y equal to 13 over 1 plus x squared, y equal to 0, x equal to negative 1, and x equal to 1. So I want to know how the graph of y equal to 13 over 1 plus x squared is going to look like. Remember, this is a rational function. This rational function has the domain of all real number lines, so I can just go ahead and say that it's negative infinity to infinity for the x values. It is symmetric about the y-axis, so it's an even function. It has no x-intercept, will never cross or touch x-axis. The y-intercept, whereas, is the point 0, 13. That's the point where the graph is going to cross the y-axis. So the y-intercept will be at 0, 13. It doesn't have vertical asymptotes. But in long run, as x goes to infinity or as x goes to negative infinity, the y value goes to the value of 0. So it has horizontal asymptote. So the horizontal asymptote is at y equal to 0. So let's think about the graph of this thing. That's my function over the x-axis. So this point where it is crossing the y-axis must be the point 0, 13 as the y-intercept. So this is 0, 13, and I have the graph of the function y equal to 13 over 1 plus x squared. Now at this point, I'm not worried about you recognizing all the graphs. If you are having a hard time understanding the graphs algebraically, then go ahead and use Desmos or GeoGebra to understand the graph before you start working on the problem. Now remember, the other boundaries are y equal to 0, x equal to -1. So this is your x equal to -1, the vertical line. And then one more point, and that should be x equal to 1. And you are talking about the region that is being bounded by y equal to 0, that's your x-axis, x equal to 1, y equal to 13 over 1 plus x squared, and x equal to -1. So this is the boundary of the lamina, and I want to integrate over this region. So remember, your next step is you try to write down the limits of the integration. So this is what we will do now. So let's first write down the limits of y. Say we're doing the integration with respect to y first. So I will start here and go all the way to this height. At this height, y is equal to 0. And at this height, y is equal to 13 over 1 plus x squared. So I get 13 over 1 plus x squared as the upper limit. Lower limit is 0. The density function I want to integrate is k. And I want to integrate with respect to y first. Then I will integrate with respect to x, where the limits are -1 to 1. That's very easy to understand. These are the limits for x values, x equal to -1 and x equal to 1. And what I will get? I will get the mass of this lamina. So the rest is just computing this integration. Recall that k is a constant, so you can bring it out, and you will get -1 to 1. When you are integrating with respect to dy, you are just going to get y because the function you are integrating is 1. And the limits are 0 to 13 over 1 plus x squared. So recall that will give me k times integration -1 to 1, 13 over 1 plus x squared dx. And that's a famous integration, anti-derivative formula. This is arctangent. I can pull the 13 out and get 13k, and then integration dx over 1 plus x squared is arctangent of x. And of course, I need to take care of the limits. Arctangent of x from -1 to 1. So I get is equal to 13 times k, arctangent of the upper limit, which is 1, minus the lower limit, which is -1. Remember, arctangent of 1 is pi over 2. And arctangent of -1 is minus pi over 2. So I get 13k times pi over 2 plus pi over 2, which is pi, and hence the mass is 13 pi k. Answers my question. In fact, I don't know what I was saying. It's arctangent of 1 is pi over 4. I'm so sorry. So all these calculations should be for pi over 4. I kept saying pi over 2, but that's pi over 4. So it changes your answer a little bit. So pi over 4, pi over 4. So 13k times, this is going to be 2 pi over 4, so pi over 2. So it's 13 pi k over 2 units. That's the mass. Once I know the mass, I'm going to find out the value for mx and my. Remember the formula for mx, you're going to integrate over the same limits, so -1 to 1, and then 0 to 1 over 13 over 1 plus x squared. And you're integrating y times k this time, with respect to y, and then with respect to x. As usual, you can take the k out, and your integration becomes much easier. -1 to 1, integration 0 to 13 over 1 plus x squared. And you are integrating y dy. So what we get? We get k times integration negative 1 to 1. Let's do the integration. You get y squared over 2. And you are integrating that thing with respect to x after you input the values for the limits. The lower limit is 0. Upper limit is 13 over 1 plus x squared. So what we get? We get equal to k times. In fact, I can bring this 2 outside as well. So k over 2 times integration negative 1 to 1. And I get 13 over 1 plus x squared. That's your y whole to the power 2 dx. So let us try to find the value of this integration. So recall, first I will square 13 and I will go ahead and get 169. So I can pull that out and I will get 169k over 2. And what we will have is negative 1 to 1, and we will have dx over 1 plus x squared whole to the power 2. At this point, we have to do trigonometric substitution. So I will go ahead and say that x is equal to tangent of theta. So x squared is equal to tangent square of theta. Then when I add 1, I get 1 plus x squared equal to 1 plus tangent square of theta, which is secant square theta. So if you look at the bottom of this integration, you actually get, so let me write it one more time, 169k over 2. And we will talk about the limits in a second. And the bottom is secant square theta whole to the power 2. So you get secant to the power 4 theta. So I can actually do that work so that we can understand what is happening. That's 1 plus x squared whole to the power 2 is the bottom of the integration. So you get secant square theta whole to the power 2. And that is secant to the power 4 theta. So that's exactly what we will get. What else? We need to understand the concept for dx. So if you derive x equal to tangent theta, you will get dx equal to secant square theta d theta. So that can go in the actual antiderivative now, secant square theta d theta. And finally, we need to talk about the limits. It's x versus theta. If x is negative 1 and x is 1, what is happening to theta? So see, if x is negative 1, then theta is arctangent of negative 1. And that is, as we have seen, negative pi over 4. And if theta is 1, then we get arctangent of 1, and we get pi over 4. So these are my new limits. Negative pi over 4 to pi over 4. So the integration is not actually terribly bad. And what we will end up having is 169k over 2. Integration negative pi over 4 to pi over 4. Recall one thing, the secant square theta on the top and the secant square theta on the bottom will cancel each other. And you will get 1 over secant square theta, which becomes cosine square theta. 1 over secant square is cosine square d theta. And that's a double angle formula for cosine. And this is the work we have seen a lot using the double angle formula for sine and cosine in multiple integrations. So we get 169k over 2. Write your cosine square theta as 2 cosine square theta. As soon as you multiply 2 divided by 2 minus 1 plus 1, because the first 2 times 2 cosine square theta minus 1 is double angle formula for cosine. So I get 169k over 2 integration negative 1 to 1 cosine 2 theta over 2. And finally, you have that plus 1/2 term. And all of that is under the antiderivative with respect to theta. So what I get is that should be equal to 169k over 2 integration, or let's actually do the antiderivative. So I will get this 2 on the cosine theta over 2, that 2 multiplied with this one. So we'll get 169k over 4. and then I will get sine 2 theta, that's the antiderivative of cosine 2 theta, over 2. That's 1 more 2. And the limits are negative pi over 4 to pi over 4. So negative pi over 4 to pi over 4. And finally, we will do plus the same thing, 169k over 4. Again, you have this 2 here, that 2 there, multiplied, they are going to give you a 4. And this integration is easier. It's integration of 1, so you get just theta between negative pi over 4 and pi over 4. Let's see what we get. So when we do sine of 2 theta, and theta is pi over 4, I get sine of pi over 2. And remember, that is 1. This 2 on the bottom I will multiply with 4, and I will get 169k over 8. As I said, upper limit will be sine pi over 2, so 1 minus lower limit is going to be sine of negative pi over 2, which is negative 1. So that's what it is, plus 169k over 4, and you will get pi over 4 minus pi over 4. So together they're going to give me, this is going to be plus 2, so when you cancel 2 and 8, you get 169k over 4. And the next term is going to give you the same thing, pi over 4 plus pi over 4 is pi over 2. So I'm going to get plus 169k over 8 times pi. Of course, I can factor out the 169k over 8, and I will get 2 plus pi. And that should be the mx. And then we are going to repeat the work to find my. So let's go ahead and do that. My is going to be similar integration. So integration negative 1 to 1, integration 0 to 13 over 1 plus x squared. And this time we are doing x times the density k, dy dx. Let's see what we get. So first and foremost, if you can understand the symmetry in this thing, there is an odd symmetry going on in this integrand, then you will go ahead and say that the integration is 0. If you don't see that, then I will show you it's actually not terrible and how to get the integrations done. So it's negative 1 to 1. You can pull out the k and you get integration 0 to 13 over 1 plus x squared, x dy dx. Since x is constant with respect to y and I'm taking the antiderivative with respect to y, I'll go ahead and say that this is negative 1 to 1, and then I will say integration 0 to 13, or actually let's do the antiderivative already. So it's going to be x, nothing to do with the integration. Integration dy is y with the limits for 0 and 13 over 1 plus x squared dx. So I get negative 1 to 1. X times, you put the limits in, 13 over 1 plus x squared dx. So recall, I can now go ahead and say that z is equal to 1 plus x squared. So dz is equal to 2x dx, means dz over 2 is x dx. Let's change the limits from h to z, and you will see why I'm doing this. Negative 1 and 1. So if I put negative 1 for x, I get 2. And if I put 1 for x, I get 2 as well. So what happens? In terms of z, this integration can be written as, you can pull this 13 out. And remember, there is a 2 under dz. So if I pull that out, I get 13 over 2. Limits are 2 to 2. X dx is dz, because we have taken care of the dz over 2 already, over 1 plus x squared is your z. I don't even care about doing this integration anymore. Limits, the lower limit and the upper limit being same, the value of the integration is 0. And you know that that is happening essentially because the x multiplier has made your integrand an odd function. And because your limits are symmetric, negative 1 to 1 with respect to x, the value of the integration essentially is going to go to 0. Even if we do not understand the odd function part, we can still go ahead and say that my in this way is equal to 0. So what it has done for us? Now we have the center of mass. Remember, the center of mass is going to be given by, so let's go back to the slide where we have done the center of mass. So, oh, I just realized one thing. The center of mass should be my over m comma mx over m. I'm so sorry. So that's the formula. This is my over m comma mx over m. So don't forget that. This is the formula. So now I can go ahead and say that using this formula, as I know the mass of this lamina is 13 k pi over 2. So we will say the center of mass for this lamina is going to be given by, let's see, remember this is my over m comma mx over m. So as we found out, my is 0, so this is 0 over m, and m was 13 k pi over 2. It's insignificant at this point. And then this one was 169 k over 2. I actually forgot. I think 8 times 2 plus 5. I'm going to go check it. So 2 plus 5. I think that's what was the mx. Let's go check this thing. So the mx was 169 k over 8 times 2 plus pi. So I think I said it right. All over the mass, which is 13 k times pi over 2. And that's going to give you the center of mass. So clearly the x coordinate is 0. The y coordinate, so I see that I can write it as 169 k over 8 times 2 over 13 k pi times 2 plus pi. So that's 0 comma, let's simplify. 13 and 169 will cancel each other, k and k will go away, so I will get 13 over 2 and 8, so I will get 4 pi. So this is 13 over 4 pi times 2 plus pi as the center of mass of this lamina.